NASA hadn't anticipated what the latest cosmic data would reveal. Hidden within recent observations lies something so extraordinary that it is compelling scientists to reshape their understanding of the universe itself. The cause: 3I Atlas, an interstellar relic older than the solar system. For weeks, it slipped unnoticed through our detection systems, nearly lost in the cosmic background. Researchers have since dubbed it a cosmic alarm bell, a sign written across the heavens. But the question remains, what exactly is Atlas? A remnant from before Earth existed, or a messenger carrying secrets we have yet to uncover? The staggering age of 3I Atlas revolutionizes how scientists interpret its existence. At roughly 7 billion years old, this comet predates our solar system by about 3 billion years. It formed during an era when the Milky Way was a vastly different environment, richer in star formation, unique in its chemical makeup, and governed by conditions we can only simulate theoretically today. Trajectory studies traced 3I Atlas back to the galaxy's thick disk, one of the oldest stellar populations nearby. This ancient region operated under physical and chemical parameters that no longer exist in modern galactic structures. Astonishingly, the comet has retained volatile compounds such as carbon dioxide and water that should have dissipated eons ago. Data from the James Webb Space Telescope has revealed the highest ratio of carbon dioxide to water ever recorded in any comet. Such preservation over billions of years implies either extraordinary storage conditions or a kind of molecular stability far beyond our comprehension. The implications of its radiation exposure are profound. 7 billion years of cosmic ray bombardment should have fundamentally altered its organic compounds. Yet complex molecules remain intact, suggesting exceptional shielding or unknown chemical processes that enable these materials to endure for cosmic timescales. The thermal history of 3I Atlas is equally mysterious. Conventional models predict that ancient comets gradually lose their volatile components due to sublimation or internal heating from radioactive decay. However, Atlas retains enough volatiles to activate when warmed by the sun. This resilience implies that its internal structure or thermal characteristics resist the usual evolutionary decay seen in similar objects. Such endurance defies standard models of material degradation, hinting either at an extremely stable, cold environment throughout most of its history or internal mechanisms capable of protecting compounds from destruction. Astronomer Luis Salazar Manzano of the University of Michigan discovered that 3I Atlas exhibits extreme carbon chain depletion, with far fewer C2 and C3 molecules than any previously measured comet. This pattern defies expectations for an object traveling through interstellar space for billions of years, where such molecules should accumulate. The classification of the comet also exposed systemic flaws in current detection methods. Initially recorded as asteroid A11PL3Z, 3I Atlas nearly went unnoticed because automated systems misinterpreted its anomalies. Current algorithms are trained to recognize familiar patterns among known asteroids and comets, which makes them prone to dismissing unusual signals as errors. The Atlas survey system in Chile, one of the world's most advanced detection networks, processed Atlas under standard asteroid parameters. Its abnormal chemical data, heat profile, and atypical activity were considered noise rather than evidence of something new. This misclassification underscores a larger issue in machine-assisted discovery. When algorithms are trained on local examples, they inherit pattern biases that can obscure truly exotic phenomena. Objects that behave outside known parameters are often overlooked unless human experts intervene. It was only through the combined expertise in orbital dynamics, spectroscopy, and comparative planetology that scientists recognized 3I Atlas as interstellar in origin. This reliance on human interpretation highlights the current limits of artificial detection methods, a challenge also faced by other major surveys like Catalina, Linear, and NEOWISE, which use similar biased frameworks that may inadvertently filter out other rare discoveries. Comparative studies with prior interstellar visitors emphasize the detection dilemma. One Oumuamua was first tagged as an asteroid before its comet-like acceleration revealed its nature, while 2I Borisov was instantly classified as a comet due to its visible tail. 3I Atlas falls somewhere in between, clearly active, yet chemically so strange that automated systems failed to place it properly. Further insights from the James Webb Space Telescope unveiled a chemical composition that defies conventional comet formation. The infrared scans detected record carbon dioxide levels, with water ice, carbon monoxide, and carbonyl sulfide mixed in ratios. Unlike any comet within our solar family, the detection of carbonyl sulfide is particularly remarkable, since it forms under specific temperature and pressure conditions rarely sustained for long cosmic periods. Its coexistence with abundant carbon dioxide hints at production environments or interstellar processing events we cannot yet replicate in models. The presence of carbon monoxide complicates the picture further. While common in many comets, its relative abundance in 3I Atlas does not match established models of ice development and protoplanetary disks. These ratios suggest that Atlas either formed under unusually cold conditions or endured radiation exposure that selectively altered its chemical makeup. Despite billions of years of cosmic ray impacts, fragile molecules like carbonyl sulfide have survived, a sign that Atlas may possess internal regenerative chemistry or unprecedented shielding capacities. Researchers now suspect that 3I Atlas originated near the carbon dioxide ice line in its original protoplanetary disk, the boundary where gas condensed into solid CO2 ice. This would explain its extreme molecular composition, but it also introduces new challenges, as most models predict this line's proximity to the parent star where water remains vaporized. Yet 3I Atlas contains abundant water ice alongside CO2, implying either a far more intricate disk structure or formation within environments where temperature gradients and chemical interactions differ drastically from those around our own sun. The protoplanetary disk may have undergone rapid cooling phases or experienced rare opacity changes that produced several ice lines at differing distances from its parent star, allowing both water and carbon dioxide to solidify together. The preservation of these compositional patterns for over 7 billion years offers an extraordinary glimpse into the chemical environment of early planetary disks around other stars. Most current models of planet formation originate from the study of young stellar systems and theoretical reconstructions of our solar system's earliest stages. 3I Atlas, however, provides tangible evidence of how planetary construction actually took place in the distant, ancient Milky Way. Global observatories are now locked in a race to capture data before this rare visitor disappears. The limited observation window for 3I Atlas has sparked an unprecedented global scramble among astronomical institutions. Unlike typical cosmic events that remain observable for decades, this relic offers only about 6 months of meaningful visibility before it retreats into interstellar space. Competition for James Webb Space Telescope observation hours has reached a fever pitch, with agencies and universities submitting urgent proposals claiming it to be the most significant cometary discovery ever. However, Webb can only observe one target at a time, and every research team wants access to this rare chance. Even within Europe, disagreements have emerged over telescope scheduling. France possesses military satellites capable of monitoring 3I Atlas in ways unavailable to civilian systems, but sharing those readings could compromise classified technological capabilities. Germany operates some of the most advanced ground-based optical arrays globally, yet their schedules are already full with ongoing projects. Italy, meanwhile, worries that rushed coordination might disrupt its commercial satellite operations. China's scientific institutions are proceeding independently, using their own unique equipment to study the comet, but withholding most data due to geopolitical tension. As a result, several research groups around the world are analyzing the same phenomenon in parallel, potentially reaching different scientific conclusions based on separate datasets. Private aerospace companies are also facing complications. SpaceX, for instance, has the technology to rapidly deploy observational missions, outpacing most national space agencies. Yet such endeavors cannot proceed unilaterally. They require government authorization, cross-border research agreements, and multi-agency coordination that take months to negotiate. Time is the enemy here. The December 2025 observation deadline has created immense pressure, since missing it would mean losing this interstellar artifact forever and waiting millions of years for another of its kind to appear. The discovery of 3I Atlas also uncovered major vulnerabilities in global space surveillance infrastructure. Our existing early warning systems were specifically built to detect objects that behave like familiar solar system asteroids and comets. Anything that moves differently or radiates in an unexpected way is at high risk of being ignored. It's like training security software to recognize only standard human movement. When something completely foreign enters the frame, it's often dismissed as an error. Asteroid tracking programs rely on predictable motion, sunlight reflection, gravitational behavior, but 3I Atlas displayed these traits while simultaneously glowing with an odd green hue and ejecting dust in directions that defied physical expectations. The Atlas survey in Chile nearly misclassified the observations as noise because the spectroscopic data defied explanation. Without the curiosity of human researchers reviewing that data, we may have overlooked one of the most valuable cosmic findings in history. The new Vera Rubin Observatory, still under construction, could improve detection accuracy once fully operational. Its design, to image the entire visible sky every few nights, means it may catch anomalies earlier, granting scientists more time to investigate. However, even Rubin's algorithms are tuned to look for predefined patterns of movement and brightness. Space-based missions like the planned NEO surveyor aim to find heat emissions from objects generating internal energy, something 3I Atlas appears to do. But those probes remain in development and are focused primarily on identifying hazardous asteroids instead of scientifically valuable interstellar objects. Ultimately, the greatest challenge lies not in collecting data, but in teaching our detection systems to recognize truly unfamiliar phenomena, rather than discarding them as irregularities. This will require a deep restructuring of how space observation algorithms process information and how we search for unconventional cosmic bodies. Further insight is coming from the analysis of dust released by 3I Atlas. The dust grains, several hundred microns in size, are far larger than those typically found in other comets. Their unusual density and cohesive structure hint at bonding mechanisms or internal material properties yet to be explained by existing cometary models. These properties may reveal how ancient comets maintained physical integrity over billions of years, reshaping our grasp of matter stability in extreme cosmic conditions. Extreme cosmic conditions, vehicles and visions, which are days, imitacidices, vololesness, volomexertive, Kidozomegrity, in extreme cosmic conditions, reshaping our grasp of matter stability in high-resolution observations captured by the Hubble Space Telescope reveal that the large dust particles within 3I Atlas maintain consistent chemical compositions across their structures, suggesting a uniform internal makeup or ongoing chemical processes that establish homogeneity throughout the comet's core. This level of uniformity is uncharacteristic of bodies formed by the gradual accumulation of diverse materials in early protoplanetary disks. The measured ejection rate, approximately 1 meter per second, indicates that the surface dust is held together by unusually strong cohesive forces compared to typical ice dust mixtures observed in comets from our solar system. This could point to unique formation mechanisms that fostered greater structural integrity, or to long-term chemical transformations during its multi-billion-year trek through interstellar space that reinforced these molecular bonds. Detailed spectroscopic analysis of individual dust grains shows elemental signatures consistent with those identified in the comet's gaseous atmosphere, but reveals concentration gradients suggesting a stratified interior. These gradients may preserve physical records of different epochs of formation or environmental transitions experienced throughout the comet's galactic travels. The size distribution of these particles also provides insight into the body's thermal history. The dominance of larger grains implies either low-energy ejection processes or compositions resistant to fragmentation under heat stress, both of which signal internal attributes markedly distinct from those of ordinary comets found within the solar system. The mystery deepens with the comet's vivid green glow. This luminous phenomenon defies traditional spectroscopic understanding. According to existing astrophysical theory, green coloration in cometary comas results from diatomic carbon molecules, yet 3I Atlas emits this brilliant hue without any detectable dicarbon, a finding as unexpected as discovering an engine that works flawlessly without pistons. This contradiction challenges the foundations of molecular physics as applied to cosmic environments. Our spectroscopic methods rely heavily on reference data derived from materials found in our own system, meaning they fail when faced with unknown chemistry from beyond. The absence of recognizable carbon chain molecules may indicate formation conditions so rare that they no longer exist anywhere nearby, or chemical reactions operating during interstellar transit unlike anything yet theorized. Either conclusion proves that our knowledge of interstellar molecular behavior remains incomplete. Adding to the enigma, scientists have identified nickel compounds within the comet's material, a startling observation since nickel typically forms under high-energy conditions or intense radiation exposure. Its presence suggests that 3I Atlas originated near a star far more active than our Sun, or that it encountered extreme radiation environments that radically altered its composition. During its galactic passage, the detection of cyanogen alongside the absence of other carbon chains creates an entirely unique chemical fingerprint that defies all current models for comet formation and evolution. It's akin to finding every ingredient of a recipe but missing the main component, yet somehow the final dish still exists. Conventional spectroscopic interpretation assumes the object's materials were created under conditions similar to early solar nebulae. 3I Atlas shows this assumption may be dangerously simplistic when applied to objects born in alien stellar regions or ancient galactic contexts. The comet's thick disk origin places it within a wider galactic framework that transforms our perception of its chemical and physical nature. The thick disk represents a family of ancient stars that formed when the Milky Way was far younger, exhibiting vastly different metallicity, star-forming activity, and chemical pathways than the thin disk where our solar system developed. Objects from this region carry the chemical imprints of an age that modern astronomy can otherwise study only through simulations and indirect evidence. 3I Atlas thus provides direct physical samples from a period when planetary systems evolved under vastly altered conditions. Its orbital implications are equally extraordinary. For this comet to have endured its journey from the galaxy's ancient disk to our current region, it would have needed to survive billions of years of dynamic motion, passing through spiral arms, dense stellar clusters, and gravitational disturbances caused by molecular clouds and supermassive black holes. The continued preservation of volatile compounds over such a long voyage implies either shielding conditions of exceptional stability or an inherent resilience against the normal chemical deterioration expected in interstellar environments. Functioning as a galactic time capsule, 3I Atlas has retained primordial chemistry that survived transformational cosmic events that should have erased all traces of its origin. Trajectory modeling supports its thick disk birth, revealing a complex orbital history that spans multiple revolutions around the Milky Way's core, each looping journey estimated at roughly 200 million years. Every circuit through the galaxy would have subjected the comet to different radiation exposures, gravitational stresses, and mediums of interstellar gas and dust. December 2025 holds monumental significance for astronomers everywhere. It marks the comet's closest approach to Earth, a once-in-human-history opportunity to study a celestial artifact predating our planet. This event offers only a brief moment to uncover secrets that could redefine how we understand planet formation around other stars. Ground-based observatories are preparing for their highest-resolution imaging campaigns yet, hoping to directly capture the comet's nucleus or even surface features linked to its astonishing behavior. Scientists are effectively observing a fragment of the galaxy's distant past, still intact after billions of years, providing evidence of how ancient cosmic materials preserve their structure. The James Webb Space Telescope has allocated specific time slots for this encounter, targeting molecular emissions invisible to Earth-based instruments. Its infrared sensors might identify trace elements responsible for the mysterious green luminescence, finally decoding an enigma unsolved by standard optical methods. Meanwhile, global radio telescope networks are gearing up to listen for electromagnetic emissions, some researchers even considering the faint possibility of an artificial origin, though most view this as extremely remote. Given the comet's unprecedented chemistry, no hypothesis will go unexplored. Throughout December, a network of international observatories will conduct continuous global monitoring, seamlessly transferring observation duties across time zones. Such coordination ensures uninterrupted data on the comet's behavior, tracking variations in luminosity, molecular emissions, and dust activity that may reveal its internal structure. Precise gravitational measurements during closest approach could determine mass distribution and density, shedding light on whether its irregularities arise from exotic materials, never-before-seen structures, or processes that operated differently in the early galaxy. This December encounter represents humanity's last direct chance to study 3I Atlas before it vanishes forever into deep space. The answers gained, or the mysteries that remain, could reshape everything we think we know about the origins of planetary systems across the cosmos.